So we've talked about sketching the root locus plot by hand, but we haven't talked about how to do it with a computer, which I did say is the preferred method when you're going to look at a system in any detail. So sketching is good for intuition, but eventually you're probably going to want to get a real plot of it from a computer. So I'll discuss how to do it in Matlab. And there are also ways of doing it in Python and Mathematica as well, but I haven't had a chance to write up notes on those yet. But MATLAB is the one you'll probably use mostly anyway. So in MATLAB, the command rlocus generates a root locus plot from a linear system model object defined by TF, ZPK, or SS. So we've used all three of these commands to build linear system models, right? TF to put in a transfer function, ZPK to put in poles and zeros, and SS back when we were making state space models. You can give rlocus any of those objects created by any of those commands, and it will give you a root locus plot. The data cursor has particularly useful information associated with it, including the gain required for the closed loop pole of a given branch to be located at the selected point. Here are a few examples. So I put these all filled in because we're going to look over in MATLAB and play with it, but then you'll have something to reference in your notes, something to look at. This part is?
Yeah, we printed them out like a week and a half ago. So.
I will check that. I will send them out to you in any case. I don't know why they're hidden. But anyways, I will send them out to you so you can see the full thing, because I think it'll be a good reference to come back to later. And like writing down code is not the most effective use of people's time, I don't think. So here's an example. Use MATLAB and ZPK to generate a root locus plot of this transfer function. So the following code generates the root locus plot. So first off, sys equals ZPK. So we define the system by saying, okay, there is a 0 at -10, comes from the numerator. There are 3 poles. They are at -5, -15, and -20, right? And the overall gain of this transfer function is 1 because there's no factor out here like 13.2. If there was, we would put that in here instead of 1.
Did you use the roots command to do that for you, or does it not work?
The roots command to find where those poles are?
Yeah.
Yes, but I think you would have to turn it into a polynomial form that's not factored.
Like a numerator denominator or something.
Yeah, so I think that you would have to expand this out. But when it's factored already, you can just read off the poles, so it's kind of like easier.
If you're given a system that's like a third or fourth order polynomial, it's not factored.
You wouldn't want to factor it. So actually the function to use then, and I think it's in this example, yeah. So like in this case, you can use the TF function, and you can give it the polynomial in the coefficients of your polynomial, and then it'll do the work for you. So it's nice. So yeah, so when you can see the zeros and the poles because it's already factored, ZPK is easier. When it's not factored, it's easier to use TF. So we build this system model, we assign it to the variable sys, and we open up a figure, and we call rlocus of sys. And we get a figure that looks like this out of it. Let's actually do it. Let's pull up MATLAB. Let's, I think I have to quit this, actually. because the screen is just to resize or whatever. So when we give these commands to Matlab, it's going to plot something that looks like this for the root locus, and it'll do the open loop pole 0 plot, right? And then we know that the root locus is going to go from open loop 0 or open loop poles to open loop zeros. There is an excess of poles in this and not enough zeros for them all to go to, right? So the poles, there are 3 of them, and there's only 1 0. Therefore, 2 of those poles have to go to zeros at infinity, right? Asymptotically. And so we could sketch this if we wanted to, but we could also use Matlab. So let's just work in the command window. Let's say sys is equal to zpk of -10. And then so that was our 0. Our poles are at -5, 15, and 20, right? And then gain of 1. So if I don't put the semicolon, it'll spit back this transfer function looking thing. And then I want to open a figure and call our locus of sys. Sys is the variable I assigned it to. And it will generate this for me.
Are we talking about something going to infinity and 0? How does that?
Yeah, so we have 3 poles, right? Open loop poles. And we say that those 3 open loop poles have to go to 3 open loop zeros. The root locus plot is going to go 2 open loop zeros. So we only have 1 open loop 0, finite open loop 0. But we say that there are 2 open loop zeros at infinity that we just can't see. And so we have we can draw an asymptote for each of those. If we were to compute it, it would turn out that the angles would be plus 90 and minus 90 degrees. And the center of that would be somewhere around -15. And the root locus plot will approach those asymptotes as it goes to infinity. Remember when we did sketching? That's how we...
I gotta watch the video. That's from last week.
Yeah.
I just wanted to make sure it's something new.
Yeah, so this is all what we looked at before, but now Matlab did it for us. And we probably would have come up with something like this for the sketch, but it might not have been perfect. Something that I do want to show on here is that if you look at the data cursor, if you click on the data cursor, and you click somewhere on this root locus plot, it pops up. Can you guys read that okay? It pops up the gain associated with having the closed loop poles showing up at that point, okay? So you can move this around and read off what gain you would have to be to make the closed loop poles be at that point. Yeah, and as you approach the open loop pole, as we expect, the gain goes to 0, starts at open loop pole, and as you increase the gain, we move out on these branches. And of course, there's one pole that comes over and goes up, another pole that comes over and goes down, so the same gain down here, so the gain up there is at 1.22 E3. So if we come down here, we can go to 1.22 E3 and see where the other pole would be, right? So this is a conjugate pole pair in the closed loop. And then the third pole is going to be somewhere in here. Let's see. Might not let me get to that specific one. Ah, there we go. So there's my gain. So these are where my 3 poles would be at a specific gain in closed loop. So it lets you see where they all are, and it lets you see what gain is associated with that. Now, the location of these closed loop poles is very closely tied to the response characteristics of the system, right? Stability, first and foremost, but also how the system gets from one state to another state, right? So the transient response and the steady state error, all of that stuff has to do with where these closed loop poles are. So now we can see for a given gain what these closed loop poles would be, and therefore maybe what the some of those performance characteristics might be. So that's what we're going to be working towards with the gain adjustment that we'll be doing soon. So this is a very useful tool. And let's take a look at the other example and what the root locus looks like there and how we construct it. I mean, essentially, getting used to looking at root locuses is useful. But also, in this problem, we want to define the transfer function a little bit differently. So, like was mentioned earlier, if it's not factored out, if your polynomial is not factored, then it actually is better to, I just noticed a mistake. It's actually better to use the TF command. I did this example without having this s be squared there in the numerator. So we can get rid of that. So you can just scribble that s out.
So you can change it like you reprint it for us, right?
Yeah. I'll fix that. Typo. There was no s squared there. So it's 4s plus 3 over this thing. So we have a transfer function where we put in the coefficients of the polynomial instead of putting in the factored out zeros and poles. And then we use, let's say we wanted to, so what is Matlab doing? Matlab is just saying, oh, we're just going to compute what the closed loop poles are for given values of gain. And we're a computer, so that's not hard to do. We can do that a lot of times, right? So like I said, numerically it's not hard to solve for the closed loop poles, but analytically it is difficult. So numerically, MATLAB says, oh, okay, I'll choose gain of k equals 5.6, plug and chug, I get my closed loop poles out. Okay, gain of 3,000, plug that in, get my closed loop poles out. And sometimes it chooses gains that aren't always what you're interested in, and sometimes it chooses too few gains because it can't compute an infinite number of them. It can only compute a finite number of them. So it chooses them, and it has a pretty good algorithm for choosing them, but it isn't always what you want. So if you want to give it an array of gains that is good for you, you can do that. And here's an example using custom gains. I decided that I really wanted to know what the root locus was with a gain of 3.5. Just specifically that number, k equals 3.5, I want to make sure that they computed that one. Because when I'm using my data cursor to go along on the plot, I want to find gain equals 3.5 in there. I also want a good number of them from 10 to the minus 1 up to 10 to the 3, so 50 of them spaced out even in a logarithmic fashion. And using logarithmic gain increments is useful because you can get up to really high gain values without having a bunch of points. So that's why we use logarithmic spacing there. And then you can also put in infinity as well, and it puts in essentially an infinite gain, and it shows you what the poles would be for an infinite gain. So you can do all of that, and then you can throw this array of just like these numbers all together, mashed together into sort, and it'll sort them so that when you give it to the R locus, it won't do them out of order. If you do them out of order, then it's going to connect to the wrong dots. So 3.5 I've just stuck in there, and I didn't want to have to figure out where it went in this log space thing. And if you use sort, it'll just find the right position, put 3.5 in there. So that was just like some idioms for doing this. I just threw into this example. And you should get something like this out of it. Which is you've got, once again, you've got two poles, open loop poles, that don't have open loop zeros to go to, any finite open loop zeros. So they have to go to open loop zeros at infinity. So you've got two asymptotes and they go off that way. So if we did this example,
Let's say it has to be like an X, whatever the gain has to be to make it into back to the stable realm. Like that's showing the path as gain gets changed. So like, unless you have some gain, you're gonna have an unstable system.
right, so these things, this one starts out unstable, right? So in the open loop, the system's unstable. But if you increase the gain, then we're going to come over into the stable range. So you do need some gain in order to make the system stable. And yeah, so we've got 7 and 25. So, and we can investigate and see. So there's my transfer function. We can investigate and see what level of gain we need to get stability. We can do that with this root locus as well. So let's look at I'm actually not going to put in the custom gains. I'm just going to use their default ones. Our locus of sys2. And we could investigate that. We could say, okay, so if I'm at a gain down here, 1.1, I'm still unstable, right? But if I increase my gain, when I have a gain of like 2.2 or so, I end up having a stable system in the closed loop. Okay? So it's a really useful tool. I recommend on the homework, when it says to sketch it, you should sketch it by hand because you need to be able to learn how to do the sketches and then check them in Matlab, which is something that you also need to be able to use. So notice from your sketch, it's kind of hard to come up with the gain. From the Matlab one, it's pretty easy to come up with the gain associated with each one. Now, when we come back on Wednesday, we'll talk about how to find those gains associated with a given point on a root locus. And that'll be kind of the beginning of our discussion of how to do design using the root locus. Okay? All right. See you on Wednesday.